Hey there and welcome. Ever wonder about sound? Really wonder what it is? Today, we're going on a little journey, following a single sound wave right from its creation all the way until it hits your ear. We're going to totally demystify the physics behind it. So let's kick things off with the most fundamental question there is.
It seems super simple, doesn't it? Sound is just all around us, all the time. But what is it really, at its core? Is it a thing? Some kind of force? Well, let's break it down and let's start with the one thing, the single thing that every sound you've ever heard has in common.
It all starts right here, in your own throat. The sound of your voice comes from your vocal cords vibrating like crazy. You can see, when they're open, air just flows through silently. But the second you go to speak, they close up and start buzzing, chopping that airflow into little pulses. And that vibration, that's it. That's the beginning of every sound.
And that leads us right into our first big idea, the vibration equation. Now, it sounds kind of fancy, but it's really just a simple, universal rule that explains every single sound in existence.
Okay, so here's the key takeaway. Sound is a form of energy. It's not a little object that flies from a speaker to your ear. Nope, it's a disturbance, a vibration, that kicks off a chain reaction. If there's no vibration, you get nothing. Just silence. And this principle is literally everywhere. Think about it. The strings on a sitar, they vibrate. The column of air inside a flute, it vibrates. That skin stretched over a drum, you hit it, and it vibrates. Even a simple bicycle bell, that metal plate vibrates. They're all totally different, but it's the same idea. Something has to shake to make a sound.
All right, so we've got our vibration, check. But how does that energy actually travel? How does it get from the source, through the air, and into our ears? Well, this is where we learn how to ride the sound wave.
Now, check this out, because this visualizes something that's normally totally invisible. As the prong of that tuning fork moves out, it literally shoves the air particles next to it together, creating a little pocket of high pressure. And that right there, that's the birth of our wave.
Now we have special names for these areas. That squished, high-pressure zone is called a compression. Then, as the tuning fork swings back the other way, it leaves a little gap, right? An area of low pressure. That's called a rarefaction. So a sound wave is really just a repeating series of these. Squish, stretch, compression, rarefaction.
You know, the slinky analogy is probably the absolute best way to get this. It's brilliant. Imagine you push one end of a slinky. That little wave of compression travels all the way down, right? But, and this is the crucial part, each individual ring of the slinky just wiggles back and forth a tiny bit. Air particles do the exact same thing. The energy of the sound zips across the room, but the air molecules themselves just kind of do a little dance right where they are.
And there's a scientific name for this type of wave, a longitudinal wave. All that means is that the particles, in this case the air, are vibrating back and forth parallel to the direction the wave is going. It's a push and pull motion, not an up and down one like an ocean wave.
So we have this wave of energy traveling through the air. But how does a simple chain of squishing and stretching create all the different sounds we hear? You know, from a deep bass note to a high-pitched whistle. Well, to understand that, we need to decode the wave itself.
Scientists like to visualize these pressure waves as this familiar wave shape you see here. It's pretty straightforward. The high points, the crests, that's our compression, maximum pressure. And the low points, the troughs, that's our rarefaction, minimum pressure. This simple graph holds the secret to both pitch and loudness. Just look at the difference here. The wave on top is all spread out. There are fewer cycles happening in the same amount of time. Our brain interprets that as a low-pitched sound. The bottom wave, on the other hand, is all tightly packed with tons of cycles. Our brain hears that as a high-pitched sound. It's really that simple.
So let's just nail this down because it's super important. The pitch we hear, how high or low a sound is determined by its frequency. That's just the number of waves that pass by each second. And the loudness we hear is all about amplitude. That's how tall the wave is. A taller wave means more energy, and more energy means a louder sound.
But our sound wave doesn't just travel in a straight line forever. It interacts with the world around it. And one of the most interesting ways it does that is by bouncing off things.
We've all heard an echo, right? You yell into a canyon and hear it come back at you. Well, an echo is simply the reflection of a sound wave. When the wave hits a hard surface, like a big wall, it can't go through, so it just bounces back, and we get to hear the sound a second time.
So why don't we hear echoes in a small room? Well, it's all about timing. Our brain needs about 1/10 of a second between the original sound and its reflection to tell them apart.
Since sound travels at about 344 meters per second, in that tenth of a second, it goes about 34.4 meters. But remember, that's the round trip, to the wall and back again. So the wall actually needs to be half that distance away, about 17.2 meters, for you to hear a clear echo.
And this idea of reflection isn't just for mountainsides. We use it all the time. A doctor's stethoscope is a perfect example. The super faint sound of a heartbeat gets captured and then bounced repeatedly off the inside walls of the tube, channeling all of that sound energy right to the doctor's ears. It's pretty clever.
Or take a look at this. In old auditoriums, before we had fancy microphones, they would put these big, curved soundboards behind the stage. It was genius. The sound waves would radiate out, hit that curved surface, and get reflected and focused in one direction, straight towards the audience.
And this is not just ancient history. It's a huge part of modern architecture. Those beautiful curved ceilings in concert halls, they aren't just for looks. No way. They are precisely engineered acoustic reflectors designed to scatter sound perfectly and evenly, so every single seat in the house gets a rich, clear sound.
So, we followed our wave from a vibration through the air, and we've even seen how it bounces off walls. But the story of sound doesn't stop with what our own ears can pick up.
This is our limit. This is our little bubble. The range of human hearing for most of us is from about 20 vibrations per second, or 20 hertz, up to about 20,000 hertz. But there's a whole world of sound that exists outside of this range. Frequencies below our range, called infrasound, are used by animals like elephants to communicate over huge distances. And frequencies way above our range, ultrasound, are used by bats and dolphins as a kind of biological sonar to navigate and hunt in total darkness. It's the same physics, just at frequencies our ears aren't built to detect.
Which brings us to a final, classic question. Based on everything we've just covered, what do you think? The falling tree absolutely creates a vibration, a physical disturbance, a wave traveling through the air. We know that for a fact. But if sound is also defined as a sensation that's perceived by an ear, can an unheard vibration really be called a sound? That's something to think about. Thanks for joining me on this journey.